Semiconductor Packaging. John D. Thomas, Alex Ruth. Book 2, Section 1, Chapter 5, Topic 1. Optimizing Power Delivery Network Design for Semiconductor Packages. Introduction.
Power Delivery Network (PDN) design is a critical aspect of semiconductor package design, ensuring efficient and reliable distribution of power to integrated circuits, ICs, microprocessors, memory modules, and other electronic components. A well-designed PDN encompasses the layout, routing, impedance control, decoupling capacitors, and voltage regulation mechanisms necessary to meet stringent power integrity requirements and ensure stable operation of semiconductor devices.
This overview explores the principles, challenges, design considerations, and optimization techniques involved in power delivery network design for semiconductor packages. Principles of power delivery network design. Power delivery network design aims to provide clean, stable, and low-impedance power distribution to semiconductor devices, mitigating voltage fluctuations, minimizing noise, and optimizing signal integrity. The following principles guide effective PDN design. 1. Low impedance. A low-impedance PDN minimizes voltage drops and power losses, ensuring efficient power delivery to semiconductor devices. Achieving low impedance involves optimizing the layout, routing, and material properties of power and ground traces, vias, and planes to minimize resistance and inductance. 2. Decoupling capacitors. Decoupling capacitors are strategically placed within the PDN to absorb high-frequency noise and provide a local charge reservoir for rapid current delivery. Proper selection, placement, and distribution of decoupling capacitors improve transient response, reduce voltage fluctuations, and enhance signal integrity. 3. Impedance matching. Impedance matching between the power delivery network and the load devices is essential for efficient power transfer and signal integrity. Controlled impedance routing, termination techniques, and via stitching help match the impedance of the PDN to the characteristic impedance of the load devices, minimizing signal reflections and ensuring optimal performance. 4. Voltage regulation. Voltage regulation mechanisms, such as voltage regulators and voltage planes, maintain stable voltage levels across the PDN under varying load conditions. Voltage regulators provide precise voltage regulation and transient response, while voltage planes distribute power evenly and minimize voltage drops across the PDN. Challenges in power delivery network design. Designing an effective power delivery network for semiconductor packages presents several challenges, including 1. High-speed signaling. High-speed signaling technologies, such as DDR4/5, PCIe, and HDMI, require tight impedance control, signal integrity analysis, and power integrity optimization to ensure reliable data transmission and minimize signal degradation. 2. Electromagnetic interference, EMI. EMI from switching events, high-speed signals, and power distribution can degrade signal integrity and affect device performance. Proper shielding, ground planes, and signal routing techniques are essential to mitigate EMI and ensure EMC compliance. 3. Thermal considerations. Power delivery networks generate heat due to resistive losses, increasing the risk of thermal issues such as thermal runaway, voltage droop, and device reliability degradation. Thermal management strategies, including heat sinks, thermal vias, and thermal analysis, are critical for maintaining optimal operating temperatures and device reliability. 4. Package size and layout constraints. Semiconductor packages have limited space and complex layouts, requiring careful placement and routing of power and ground traces, decoupling capacitors, and voltage regulators to optimize power delivery and signal integrity while minimizing parasitic effects. Design considerations for power delivery network optimization. To optimize power delivery network design for semiconductor packages, several key considerations must be addressed. 1. PDN topology. The PDN topology, including power and ground plane arrangements, routing layers, and signal return paths, significantly impacts power distribution efficiency and signal integrity. Proper PDN partitioning, layer stack-up design, and signal isolation techniques are essential for minimizing impedance variations and reducing crosstalk. 2. Decoupling capacitor placement. Decoupling capacitors should be strategically placed near the power supply pins of load devices to minimize loop inductance and provide local charge reservoirs for fast transient response. Distributed decoupling, staggered capacitor arrays, and optimal capacitor placement techniques enhance noise suppression and improve power integrity. 3. Power integrity analysis. Power integrity analysis, including transient simulations, voltage drop analysis, and impedance profiling, helps identify potential voltage droops, noise hotspots, and signal integrity violations in the PDN.
Advanced simulation tools and analysis methodologies enable engineers to optimize PDN design parameters and validate performance objectives.
4.
Voltage regulation mechanisms. Voltage regulators, such as linear regulators, switching regulators, and voltage reference circuits, are employed to regulate and stabilize voltage levels across the PDN. Proper selection, placement, and tuning of voltage regulators ensure accurate voltage regulation, transient response, and load regulation under varying operating conditions.